Okay, so uh, today in this presentation, I'm going to discuss four very basic questions about optical communication. So the first question is, why do we need fiber optical communication? And then where do we use fiber optical communication? What are the state of the art and challenges that we are facing? And how will the technology evolve in the coming years? So basically in this talk, I just like to give an overview about what's happening in the landscape of optical communication. I will focus mainly about the technologies that either are commercially available today or will be available in the coming years. So before going into detail, I would like to give one very quick slide promotion about Nokia Bell Labs, the place that I am working right now. And Nokia is a Bell Lab, or just Bell Lab, is a very special research and institution in telecommunication with a quite long history. It is was founded almost 100 years ago, and it has been responsible for some of the most important innovation and invention in the 20th century. Such as the transistor, the digital communication, the first communication satellite. So it's a pretty amazing place to work for. So please consider Bell Lab in your next career move. So let's go back to the topic. So the first question I would like to discuss is, why do we need optical communication? What is special thing about that? So what you are seeing here is a picture showing a simplified map of the global optical communication network. So this is truly the backbone of the internet because it's carrying more than 99.99% of the global IP traffic. So this is pretty important for our economy and our life. And to build it, network, more than 3.5 billion kilometers of optical fiber has been installed. And this means that more than half a kilometer of the optical fiber for each and every one of us. So it's pretty amazing. And every year, we keep installing more than 300 million kilometers of optical fiber to cope with the capacity growth. But still, with that, even with the giant network, we're still facing some a lot of challenges and pressure because the global IP traffic it keep growing exponentially with a compound annual growth of 30% a year. And you know that we cannot pay 30% more for communication service every year. So there is a lot of pressure to grow the network while keeping the cost low. And this is exactly where we need fiber optical communication. So why only optical fiber can support that kind of traffic? If you look at here in 2021, the total IP traffic exceeding 250 exabytes per month, meaning that more than 50 gigabytes for every one of us. So why only optical fiber can support that kind of traffic? So why do we use light wave for communication? So all communication systems are based in the same principle that we embedding information, or we say modulating information on the amplitude or the phase of an electrical magnetic wave, so of an electrical field. Shannon tells us that the capacity or the maximum information rate that we can transmit through a certain channel depend on the bandwidth, or which is the frequency range in which we can use for the data modulation, and also the signal to noise ratio. And in reality, there's always a constraint on how much power we can get out of the transmitter, and also there's fundamental limit on the noise. So the signal to noise ratio is something there is a limit. There is a limit on that, and you can see that it's sitting inside the log. So its impact on the capacity is smaller than the impact of the bandwidth. So if we want to design the system supporting terabit per second, the first thing we need to look at is the bandwidth. So if we want to have a wide bandwidth, and obviously we need to move to the higher carrier frequency, because if we stay in the baseband communication or even in the millimeter wave range, we have only a few tens of gigahertz usable bandwidth. which is not enough for supporting the global telecommunication network. However, if we move to the higher frequency, such as 200 terahertz in the optical region, certainly we have 40 terahertz of bandwidth for data modulation, which is thousands of times higher than the bandwidth we may have in the low frequency region. And also in the 1960s, the laser was invented, and it provides a very effective way for generating light, a coherent beam with a focus, and we can, it's very important because the focus beam travel very far. So we know how to generate signal at this frequency range, and the laser provides a way for generating the coherent beam, which is needed for communication. So this is the reason behind we move to the optical frequency range here. So now we know that we have the light source. What we need for building a telecommunication system is the waveguide. And the optical fiber is the waveguide, which guides the light from the transmitter to the receiver. And in reality, there's many varieties of fiber, but the most common one is a standard single-mode fiber, as you can see here, where we have the fiber core with around 8 to 9 micron in diameter. And we have the surrounded by the cladding with the material with slightly smaller reflective index. And with this design, the light you can find within the fiber core through the total reflection effect. So what is special about the optical fiber? So the optical fiber is made of glass or silica, and this material is very good for transporting light because it absorbs very little light. And because of that, we can manufacture the fiber with extremely low loss of 0.2 dB per kilometer. And this means that the light travel over 1 kilometer lose only about 5% of the optical power, so it's pretty low. But it's not always been that way, because the fiber actually was invented around 100 years ago. And back in 1960s, the loss is still 1000 dB per kilometer. And the industry has made tremendous progress to bring the loss down to the value we have today, which are below 0.2 dB per kilometer. So you can see that when we make the progress from here to here, it means that the industry has reduced the loss by a factor of 10 power 100, which is a normal number, because the total value of the total number of atoms in the universe is just 10 power 82. So this is tremendous. So I don't know any other technology that makes such kind of improvements in its invention. This number is huge. So now, if you compare the fiber with some typical coaxial cable for RF communication, you can see that for the RF cable, the loss is for the good cable is about 0.2 dB per meter. So so the fiber is 10 power 20 times better than one of the best coaxial cable. And you can see that the cable, RF cable also have the bandwidth, right? Because the attenuation increases with the frequency. And this is exactly what the limit the bandwidth that we can use to transmit the signal through the coaxial cable. And that is why such kind of cable cannot support the wide bandwidth signal and huge capacity. And also, the cost of the fiber is incredibly low, which is about 8 cents per meter. And the cost and the amazing low loss here are the key factor which enables the wide adoption of the optical fiber. So now the second question, where do we use fiber optical communication? So you can think that the network is just the interconnection of boxes which perform the function of switching and routing. So optical communication, you can think it in the same way. We use optical communication to connect boxes or switches and router. And in general, because optical communication provides the huge bandwidth and over the long distance, and it is used for connecting boxes across the country and across the continent. And today, we also use optical communication for a short-reach system, which is just 10 meters or a few meters within the data center or within a few kilometers in the access network. And obviously, we need such kind of capacity for metro network and for long-haul and undersea network. So there is a wide range of applications for data center interconnect, data center network, for the access mobile fronthaul network, and for the metro network, and for the undersea network. And because I mentioned these three network segments, because they have a different requirement in terms of capacity, in terms of reach, in terms of size and power, in terms of cost per bit, and because all the constraints will define the optical communication technology for each segment of the network. And this is what we will talk about later on in the presentation. So now let me discuss a little bit about the optical transmission technology, state of the art, and the challenges that we are facing. So there are a variety of communication techniques in optical communication, but there are two main transmission techniques. But before going into detail, I would like to talk a little bit about wavelength division multiplexing, because it is very important in optical communication. So in optical communication, we have, of course, we have the transmitter which modulates the signal onto the optical carrier. So basically, we have the modulator and the laser. And in many cases, the laser can be the modulator itself. So we have a signal processing which encodes the data to generate the analog signal to be fed into the modulator. But now, I mentioned 40 terahertz of optical bandwidth, but there's no way we can use that at once. So what we do is that we use many transmitters operating at a different wavelength, and then we multiplex them together, as you can see here, to fill up the bandwidth. And because optical communication can be used for long distance transmission, over 100 kilometers and so on, we need to amplify the signal because attenuation is still getting too high. And the most efficient amplifier operating in the C-band provide around 5 terahertz of bandwidth. So the availability of the amplifier defines the transmission scheme, right? Because we have amplifier provide 5 terahertz of the bandwidth, and this is how the system is built today. So as a receiver, of course, we need to demultiplex all the channels to separate them, and then we convert them back into the electrical domain for the signal processing. And the signal processing today can compensate for the impairment of the fiber channels, such as the chromatic dispersion, the fiber nonlinearity, and the polarization mode dispersion, and so on. So now there are two main transmission techniques. So the two main techniques for modulating the signal onto the line wave carrier. So the first technique, which is the most simple, the simplest one, is intensity modulation. So basically in the technique, we modulate only the intensity of light, but you can see here that the 4 levels of the intensity, which corresponding to 4 combination of 0 and 1, this is how we encode the information. And so at the receiver one, we have the photodetector, which exactly detecting the signal intensity. So the system is very simple, one modulator, one detector. And in many cases, the modulator, as I said, can be the laser itself. However, we need to pay the price for this simplicity because, as you know, when we do amplitude modulation of the carrier, we have the signal at the above and below the carrier. We call that upper sideband and lower sideband. And in the ideal case, without any chirping, the lower sideband would be the complex conjugation of the upper sideband. So this is a perfect relationship. However, the fiber has a phase response, as you can see here, which has a quadratic phase response, and it will destroy the perfect relationship. And after fitting as a photodetector, some frequency are canceled out. So this is a famous Bio-fading effect. So this imbues the bandwidth to the fiber in this very simple transmission scheme. And this bandwidth here depends on the transmission distance. So with that transmission scheme, we cannot travel very far. The system cannot reach very far unless we know how to manage the dispersion of the link. So this is a limitation. So for that system, people prefer to stay in the O band, where you can see here the dispersion dependency on the wavelength. And in the O band, around 1310, the dispersion is 0. But you know, it depends on the wavelength, so it's not exactly 0. But here the dispersion is very small. And if we can avoid dispersion, the transmission speed of that system can be increased by increasing the speed of the modulator. And this is exactly what people have been doing until 2006. And you can see here, by increasing the electronic speed and the speed of the optical modulator, or modulating the laser faster and faster, people can reach 100 gigabit per second back in 2006. And this line here shows a 30% increase per year. So this is what is needed to cope with the capacity growth. But and then at 100 gigabit per second, everything becomes challenging. So with the direct detection, we cannot keep up with the growth of the capacity and follow the trend anymore. And then coherent detection system came along, so people need another technique for using the bandwidth more efficiently. So today, the IMDD system is used only for short-reach system with distance below 10 kilometers, and we can use a few wavelengths here in the O band. If we use too much wavelength, you can see that we need to cope with the dispersion again. So, like I said, to further increase the capacity, we need to use the bandwidth more efficiently. And this is a coherent detection system came along. So basically, in this system, we modulate the phase and amplitude of the light wave, where you can see that we have the quantum constellation here. So basically, we can modulate the phase and the amplitude simultaneously. And also, the light wave supports the two orthogonal polarization, and we can use them to modulate the light simultaneously too. So you can see that we can build a modulator like that. Instead of having one modulator, we have 4 modulators. So here the 2 modulators, you can think of that like the in phase and quadrature, or the phase and the amplitude. And we have the 1 polarization, 2 polarization. So we have here 4 data streams. And so we can have 4 times the capacity within the same bandwidth, or we say 4 times higher spectral efficiency. For detecting that signal, we need a more complicated receiver. As you can see here, we have the front end. So basically, we mix the signal with a local oscillator, and when they beat at the photodetector here, they bring them in the baseband, and through this beating with optical hybrid here, we can detect both the amplitude and the phase of the light wave in X and Y polarization. But they mix up during propagation because of polarization rotation, because of chromatic dispersion. So we need to have some signal processing for decoding the symbol and the bit. And this is a tremendous progress here on making the DSP ASIC more efficiently, more powerful. And now today we can use it signal processing to cancel out all the chromatic dispersion, unlimited amount of dispersion. So we can extend the reach beyond even 10,000 kilometers. So this is a much more powerful transmission technique. But as you can see from the block diagram, is a much more complicated, both in the hardware and in the signal processing. So with the introduction of the coherent detection in 2008, the first commercial coherent DSP ASIC was in 2008. We can continue the trend here, and today in research, we can achieve more than 1.5 terabit per second per carrier in the coherent detection system. So it's pretty amazing, where you can see that here did the point for the direct detection. And today we can achieve about 300 gigabit per second per lambda. Now, just to show you a little bit about what is commercially available today. So today, the DSP ASIC in the product can achieve 800 gigabit per second per wavelength. And if you can look at here, the figure shows the progress of Ciena on their coherent DSP ASIC, where you see here, this is a receive signal to noise ratio. The black curve here is the linear channel limit. So this is what can be ultimately achieved using the DSP ASIC architecture that we have today. And here's a client red, and you can see here's the black one is the first or second generation, the third generation, the fourth generation, and what they have today. And you can see that we have made a tremendous progress in closing the channel gap. So if you see that even with the fourth generation, the gap from the actual product to the channel limit is more than 10 dB, and today it's around within 2 dB. So this is tremendous. And the figure shows the layout of the chip of the DSP ASIC, and it built in 7 nanometer CMOS, and it can perform 800 tuning operations per second. So it is about 400,000 times more powerful than our laptop. So it is pretty amazing, and people selling the chip for a few $100. So it's amazingly how cheap that is. So, and also this is what we can achieve with a single wavelength. So if we multiply many wavelengths together to fill up the C-band, then of course we have the more capacity. And this is the trend in the WDM system where people just fill up more and more wavelength, and then people turn into the coherent detection system to further increase the capacity. And today the commercial undersea system can reach about 30 terabit per second, and some are planning to have about 50 terabit per second across the ocean. So it's really what is needed to support the IP traffic flow. So now let me talk a little bit about what are the challenges. Obviously, we have the 3 network segments here. We have the short wave within the 10 or 20 kilometer. We have the metro network within a few hundred kilometer, and we have the long haul network. And they have different requirements in terms of capacity and in terms of cost. For the short wave system, today's dominant technology is the most simple, is the simplest one, which is IMDD. And the challenges moving forward is, of course, to increase the capacity or to get the right capacity, because if operator want to upgrade to 100 GB per second, they just need 100 GB per second, and it will stay there for 10 years or so. But more importantly, we need to have the right footprint and power consumption with the lowest cost. So the priority here is the footprint and the power consumption and the cost with the right capacity. So for the metro network, today we use coherent detection, and the requirement for that network is of course, we need to increase the capacity, we need to have the, we need to meet the reach, and we need to increase the flexibility, because as the network grows, managing the network becomes more and more challenging. So, and for the long haul network, the requirement has stayed almost the same over the 30 years, that we need to have the high capacity, because we need to connect a country and continent with a huge capacity, and laying out fiber is very expensive, because they run across a few thousand or even 10,000 kilometers. So because of the limited number of fiber, the requirement on the capacity is a priority. And obviously the reach is very important. And also in all the cases, the differentiation is to get the lowest cost as the highest capacity. So now let me talk about what is happening in the 3 network segment, the technology change to meet the challenges that I just mentioned here. So this is what we're going to discuss now, how the technology will evolve in the coming year. So let's talk about the first segment, which is a short wave. Because in short wave, we have a few applications. We have the data center, we have the mobile fronthaul, we have the access, fiber to the home, we have the passive optical networks, and many applications. So I just want to mention one application for you to see how people or industry are trying to meet the requirement. So let's talk about hyperscale data center. So data center is a place where the giant web scale company like Google, Facebook, Amazon store their server, and they processing our request. So today data center is huge. A data center can be bigger than a few football field combined. And actually the traffic within the data center is more higher than actually the IP traffic going out of the data center. As you can see here, the worldwide data center traffic is now about 6 times higher than global internet traffic. So you can see that most of the time the traffic never leaves the data center. So, and the data center, of course, is very expensive. To be one data center, people spend more than $1 billion because it's huge. It contains more than 1,000 servers and 1 million optical transceivers. And actually, in terms of networking spending, the optical connectivity contain cost about 60% of all the networking spending. So that is why the cost is very important, because within the data center, millions of optical transceivers connected to switches and routers to build the network. So the cost has become very important. So now if we go a little bit deeper in the data center interconnect, data center network, today from Microsoft, you can see that simplified block diagram here. So basically they have the many server, they stack together, or we call it rack. So the server is where the data is stored, and then on top of the rack, we have the top of rack switch. And then we, after each row or column, we also have another switch, and it go to the switch for for the block or building also, and then it go out of to the data center. And today only people use 50 gigabit per second to connect the server to the top of the switch, and above that, the requirement going forward is 400 gigabit per second. So people need 400 gigabit per second to connecting this switch. And from the tier 1 and tier 2 switch, they also need 400 gigabit per second. So 400 gigabit per second is a requirement for the network connectivity in the data center. And obviously, it follows the Ethernet switch speed. And in the future, we were talking about 800 gig and even 1.6 terabit per second. So as you can see here that we have millions of connections and each need 400 gigabit per second. So it's a pretty demanding. So now if we look inside the data center switch box, because like I said, everything here is a connecting boxes, right? It is a switch box, it is a switch box, and it go out to the regional network, and it go out to the long haul network. So now inside the data center switching box, you can find that the brain of the switching box here is an Ethernet switching ASIC. So basically what it does is that it's switching packet from one port to another. And then within the box, we have the front panel. And here we have the optical transceiver is plugged to the port. So this is a conventional approach. And it is a very good approach because the switching the switch vendor can manufacture the switch at very high volume, and the optical vendor can do the optical transceiver. And obviously, you can plug different type of optical transceiver here with different reach and capacity, as long as they meet the form factor requirement here. So now you can now this model has been working very well for many years. But now we are facing the challenge. And what is the channel? So the challenge here is that we need to move the data from the switch ASIC to the front panel to go to the optical transceiver. And at 400 gigabit per second, we need to burn the power to move the data from here to here. Even from here to here, just 20-something centimeter. But it's still the challenge. It's a big challenge when we increase the capacity. And also, even though the optical pluggable transceiver is quite small, but it's not small enough. And you can see that when you fill up on the front panel, it blocks the airflow from inside. So cooling the switch ASIC become another big challenge. So now, what is the technology change to solve that problem? So as you can see that today we have the Ethernet switch and we have the pluggable optical transceiver in the front panel, and we need to connect them through the PCB. And the next thing to do is that because moving the data from here to here burn power, and the to solve the problem, what we can do is that we can put the optic very close to the ASIC switch. So we reduce it, the distance here from 20 centimeter to a few centimeter or even less. And the next thing is that we can put them even closer together. And this is a way to reduce the power consumption. So this is the trend that now the switch vendor will need to co-package their switch, their DSP, their switching ASIC together with the optic. And this is how the way people move forward to reduce the power consumption and also to increase the density of the switching port. So the goal and the purpose is to reduce the power consumption and get more data out of those in and out the switching board. So just to show you one example of the demo from Intel just 1 year ago in their switching board using the co-package technique. And you can see that now the front panel is quite empty because the optical connector is much smaller than the pluggable transceiver. And this is just the beginning, and I think that in the near future we would see more and more co-package board like that. So now we move to the second application, which is a metro and long haul network. So like I said, the optical network is just a high capacity network to connect router together, right? So we have here router in one place, and over we need to connect them with another router sitting, let's say, a few hundred kilometers away or even 1,000 kilometers away. So we need to connect them to the optical network. And the problem is that the router here has the slot here has we can plug the optical transceiver in, but the pluggable transceiver is usually small, and we use IMDD technique here to minimize the power consumption, so we can put the transceiver inside it, a small form factor pluggable. So they will not get from here to here. And to do that, we need what we call the coherent transponder box that you can see here. We have the client interface and the line interface. So basically, it's convert the signal back to the electrical domain and then use a coherent technique to transport this signal. So this, you can think of that is in like a bridge. And this is exactly the box sitting here, and this is what we are doing for living. However, when we grow the network, the box here is annoying because it's expensive and it's a redundancy. So what if we can connect the router from here to here directly? And we can do that if we can boost the if we can make the coherent transceiver small enough, consume less power, consumes more enough power, so it can be put in this small form factor. So reducing the power and the size of the coherent transceiver is a key to do that. And this is exactly what is happening right now. Then we are entering the era of pluggable coherent optics. Like I said here, we want to connect the router to that router, and we want to remove the transponder board. So we can do that if the coherent transceiver is small enough, so we can put them into the pluggable module. So we can plug them directly to the switch. So this is a trend that people are trying very hard to reduce the power consumption of the DSP ASIC, and with the optical integration to reduce the size of the photonic integrated circuit, so they can be put into the small form factor pluggable here. So this would simplify the network in a significant way. And this is a trend that we see. It will change the landscape of optical communication a lot. So now we move to the third application for long haul and undersea network. And as I said, the main requirement here is the capacity. And we currently have already exhausted the C-band. The C-band that we're sitting from here because of the efficient amplification scheme. So, but we have used all of the bandwidth. And the room for improvement is only within 2 dB, so which is not enough for supporting in the long term the capacity growth. So the question is, how do we increase the capacity further? one obvious approach is to move to the other band. We can move to the S band, L band, E band, U band, and so on. So we can keep reuse the fiber infrastructure. However, the component like amplifiers, the laser, the multiplexer, and so on for this band are not mature enough and they are not low cost. So there are a lot of hesitation in moving even in the L band. And also this is not a long-term solution because the fiber doesn't lie when we use more than 13 terahertz of continuous bandwidth because of the Raman effect. So there is another trend that we can deploy new fibers and no one can prevent us from deploying new fiber. Of course, there is a cost of doing that, but the fiber is cheap. And when you deploy fiber, you can deploy thousands of fiber. So this is a very long-term solution. You need to make a big investment, but once you make the investment, you can be fine for 50, even more. So this is a very attractive trend. Or people can use a different type of fiber, but still you need to deploy new fiber, right? It's just a more efficient type of fiber, more compact, like you put more core within a cladding. Or we can use a multi-mode fiber. But later on, people realize that there's many trouble with using multi-mode fiber. So using parallel fiber or multi-core fiber may be the way forward, because then the capacity would depend on the number of fiber. And you can put a multiplication factor here to scope with the capacity growth. But then if you have too much fiber, then we can the technology would need to modify a little bit because the cost will be the most important then. So this is the trend coming. We will see the people moving in the different band, a little bit in L band for the next 5 years or so. But in the long term, people will deploy new fiber. So with that, I would end with a very quick slide on why I think wireless researchers also should care about optics. So in optical communication, wireless communication is very important for us because we are doing a lot of digital signal processing, and many problems that we are solving actually has been solved in different contexts in wireless communication. So we always care about wireless communication, but now is the time I think that wireless research also should care about optics. Why? Because people use more and more optical communication. So today we use that for connecting the radio tower to the center office or distributed office. And so with the advance of massive MIMO 5G, and in the future we move to the even higher frequency, and the capacity coming out of the radio units would be much higher, and only optics can support that. And more importantly, there is a trade-off between the power consumption that we do as a radio unit versus the fronthaul capacity. So if we do a lot of signal processing in the radio unit, we can reduce the fronthaul capacity, but it is not the one we want to go, because when we deploy more and more radio units, they need to be lightweight, they need to consume low power. So actually we want to move in the direction, right? Then we need to care about the fronthaul capacity. So then the core integration of the optic and at the radio units will be very big in the future, because it is the only way we can reduce the power consumption of the radio unit. So in my opinion, optic is defining what functionality should be placed at the radio unit. So the two communities should work together to find the best integration approach. So with that, I would like to thank you for your kind attention.